I'm Rob May, the CEO and co-founder of Neurometric.
And I'm Cooper, COO here at Neurometric. We're co-founders, and this is Inference Time Tactics, a podcast for builders, researchers, and engineers who want to understand what's really happening in this next era of AI.
We're building the inference optimization layer for AI, and that word inference is doing a lot of the work because the next performance gains in AI aren't just about model size or training data. They're about how we use reasoning and thinking algorithms at runtime.
And in this episode, we're joined by one of our co-founders and CTO, Byron, to talk about the illusion of thinking, what it reveals about reasoning models, why we built a tool to explore it, and what it means for AI developers, researchers, and policy. So let's get into it. Let's start with the basics. What is the illusion of thinking paper, and why did it catch our attention as a team?
I think part of the reason this paper was so popular is, number one, it came out of Apple, and Apple doesn't publish a lot of AI research. And so it's been interesting to watch just, that aspect of the response. But what caught the attention of so many people was so most of these reasoning tasks are done on like coding and mathematic benchmarks. And this paper sort of looked at reasoning from some different puzzles, which we'll talk about. And the conclusions of the paper, and we'll talk about whether those are right or wrong, but the conclusions of the paper were that these reasoning models don't have more generalizable reasoning capabilities beyond a very simple complexity threshold. And that there's likely this sort of like inherent limit in these models because as they try to solve these problems and they spin and they reason, like at a certain point, they seem to give up or not get any better. And it's interesting. This paper has received a lot of attention in the press over the last 4, 5, 6 weeks whenever it came out. Some people saying like, this paper's crap. It doesn't really show anything. They did all these things wrong. And other people saying this shows the limits of those models. They're not going to get us to super intelligence. So it's been a pretty important paper. And it's a little too technical, I think, for Cooper and I just to digest it. So that's why we brought one of our other co-founders on today to talk about it. So Byron, you want to dive in and give an overview of the paper from a technical perspective?
Yeah. So, I think as Rob just said, the findings of this paper were very controversial. And I would say rightly so, because from a academic scholarly perspective, there were issues with some of the experimental design, but we're not going to get into that. That's been discussed quite a lot. I'll pick a few things that I think are worth highlighting here. So the first thing that I think is really important to just make sure we all kind of understand is, what are these large reasoning models and why did they do this study in the first place? So a large reasoning model is really a large language model, right? It's just been specially trained to have sort of two phases. One is this reasoning or thinking phase, and the second is the normal output phase. And the way it works is, the idea is that you give it a prompt. It's then supposed to kick into thinking, which it creates a little thinking token. It says, I'm thinking now, right? And then it essentially has been trained to think out loud, as if you were asking someone in a math or a coding challenge to describe their process and how they'd solve a puzzle, as opposed to just doing it themselves with language. And so it generates this stream of tokens. Then eventually it's supposed to produce a stop token. I am done thinking. And then it moves on to the actual output. And so the way you can think about what they're doing is it's dynamically augmenting your prompt. It's trying to help make your task easier to solve by creating this on-the-fly stream of additional context that can be used to solve the answer. But because that is sort of fuzzy and messy text, it isn't necessarily needed for the output. It's hidden by most of these models. And you'll see like an experience as it's thinking, right? But it's really just generating tokens. Just they're invisible to you because they're not needed for the output. And so that's what these reasoning models are doing. And so the researchers at Apple wanted to probe, how does that reasoning chain what does it do? How does it evolve as the complexity of the task gets bigger? And so they picked these sort of very simple to describe logic puzzles of varying degrees of computational complexity in their answers in order to have this repeatable experiment. And so they did that. They found a couple of kind of major findings that they put out there. One was that there were these regimes, right? That sometimes reasoning doesn't help you at all. It actually is detrimental both either in terms of cost, because you have to generate more tokens, or it actually gets things wrong because it's overthought the problem. There are cases where reasoning absolutely is necessary, that it just completely blows away any attempt at a non-reasoning style model. This reasoning really is important. And then there's a threshold where no amount of reasoning seems to make a difference. And I think that's a really important takeaway. And I think that's a valid finding. Now, you can argue, and people have, about, is that meaningful? So for instance, people have taken issue with the prompts that they created. They've taken issue with how they've tried to solve the problem. So for instance, you can absolutely solve the Towers of Hanoi for arbitrary size if you just tell the model to produce a program that will solve the model, as opposed to having it think through and try to produce some textual representation. And so the highlight takeaway here is that, one, you do need to understand your problems. And I think that's what this showed, that the problem you're trying to solve is important and different models will work differently. Two, I want to go back to that point about how things sort of stopped, right? This almost paradoxical result or non-intuitive result that as things got really hard, the models sort of stopped. They almost gave up, it felt like, or it just sort of decayed. And this has been also pointed out that in some cases, these models have thinking token budgets. And they didn't present this in the paper, but you only get maybe 10,000 tokens worth of thinking before it says, okay, we're done. Let's move on to the output. And for some of these models, there's no way that you could think through it the way they've designed it to not fit within that budget window. And so everything outside that budget just got cut off. And so stuff just didn't work.
Byron, does that last point tie to some of the commentary on this talked about how the models would sort of like come up with a series of steps to solve the problem and determine that chain of steps was too long, and therefore they would like sort of look for a shortcut. Is that tied to the token
kind of
availability or something else?
I would say it's something else. I would say there's sort of this hard limit of thinking that can happen, but it's tied to the reason of why does that budget exist in the first place? And the reason the model providers, so if you're using this through an OpenAI or an Anthropic or Together, any one of these sort of inference providers, a well-known phenomenon with these reasoning models is that, like I said, they need to at some point produce that I'm done thinking token, and sometimes they don't. Sometimes they just keep going, and this is very apparent in the small models. Like if you were to go get a Qwen 3 model, for instance, and like a 4 billion or 8 billion model, and we've seen this, like it will just run forever. The only way to stop it is to literally kill the program if you have not imposed some other safeguard. And this can happen where the model's like, okay, and this is one of the findings they did come up with, is that sometimes the model would, in its reasoning trace, get to the right answer, but then it would not stop. It would keep going. And then in that continuation, it would start to mangle and change things, and then it would go off the rails. And so it is kind of tied to that idea that sometimes the models will start to run, but then for whatever reason, again, they're all fairly inscrutable in how they were trained and the stochasticity of these, they eventually get stuck in some pattern where they can't escape, or they produce some sequence that says, oh, wait, this is too complicated. I'm trying to optimize for elegance and simplicity. So let me try to find a simpler solution when there isn't a simpler solution, or it's unnecessary for the task at hand. And so these things are very hard to control. And so really the only hammer, we have one hammer, which is to just stop and impose a budget. And that's one way that people do it. There are others, and people are researching this, but how to know when the reasoning is efficiently done is an open research question.
So we built a tool to explore this. What exactly is this illusion of thinking tool? Why did we build it? What can people do to use it?
Yeah, so as part of this conversation, we really, a lot of us were probing this and having these conversations about what this means. And so we thought it'd be really cool to say, well, we've been looking at, again, local models and sort of the boundaries and capabilities of local models, small models that you run on, say, a laptop via a llama. And so I had this idea of, well, what if we took that paper and re-implemented it sort of as a reproduction study almost, but to bring the tooling around and say, here, you can actually now run this study or try this, what they did, try it out for yourself, but on any model you'd like. And in this case, we focused on the local models to see how they behaved. And so, as I mentioned earlier, we tried it with things like the Qwen 3 family of models, which are sort of local models that you can download that have this sort of reasoning capability baked into them. And so we built this. We built it using Gradio. Shout out to Gradio. It's a really nice library from Hugging Face that allows you to build up really simple but nice sort of demo environments to interact with models. And so it's quite nice. It gave us a nice way to build these up. I took all of the information from the appendix of the paper, where they actually described all the prompts that they used and the sort of details, put them into this. And so we sort of took everything out of the paper, sort of reproduced it as a standalone tool for people to play with. And I think and this is available, it's open source. You can come download it from our GitHub repository. But just doing that and getting that additional hands-on intuition was actually really valuable for me personally. And just, I think anyone who is thinking about building tools with these reasoning models or even local models, it kind of helps you see what they're doing. And by being able to see that thinking process, that reasoning trace, it helps you also understand kind of what the limits of it are and what it actually looks like. And so an example, Qwen 3 4B model on like even a simple like 3-disk Towers of Hanoi, it would start to do it. It would continue on, and we have it displaying the thinking trace so you can see it evolve in time, and it would get stuck. It would literally just repeat the same paragraph over and over and over and over and over and over and over again. I had to kill the program because it just would not stop. And each time it was only like a slight variance. So this is where, if you're a builder, if you're a practitioner, having hands-on experience, even with little sort of toy examples like this, is really great for building insight into what the reality of these models are.
Yeah, I think that's an important point, because when, as people are starting to think about, we talk about this agentic world and all the things that these models are going to do, and they have really impressive capabilities, and they're getting better all the time. But I think it's become complicated for people, sometimes even technical people, to figure out which model to use and how long to let it think and what kind of things to do. So it's going to be interesting to see if over the next months to years the industry starts to develop more of a. There's not a lot of intuition on sometimes how these things will work on certain problems, and it's definitely not as well understood as, say, the engineering intuition of making changes to a system in some of those ways. So it's going to be a really exciting time to watch.
And what surprised you most, or what are some of your opinions on this illusion thinking paper?
One of the things I found, fascinating was sort of the discourse around it. So the paper, like I said, really set out to try to interrogate the behavior of the reasoning trace. What does it look like? How does it work? And one thing they found, and we mentioned it before, but one thing they found is that it does get the right answer sometimes, but then it doesn't. It doesn't know it has the right answer, because it doesn't. My opinion personally is that these things don't know anything, right? They are next token predictors. There's a philosophical argument here that's not relevant for this conversation, but it has no way of evaluating really if what it has produced is sufficient, if it has completed, the task, or if it needs to keep thinking or keep reasoning. And so we see this, that's, I think, demonstrated here to some extent by the fact that it does find that it gets a certain degree of the way through the task successfully in these intermediate steps. And then it makes a mistake, but it doesn't know that it made a mistake. Because again, it doesn't really know anything in that sense. And it doesn't work, so then it gets stuck and it gets off the rails, and oftentimes it can't recover. So I think that just having that validated in this way was interesting. I think that a lot of people, and I think I mentioned this also, a lot of people got real nitpicky about the outcomes. So again, the story here is to understand how reasoning helps you in larger complex environments. But some people got real fixated on the task itself. So like I mentioned, Towers of Hanoi, if you just wanted to solve the problem, their way of solving it was not good. It was very suboptimal. If you just wanted to have a thing that could generate a solution to the Towers of Hanoi, people demonstrated you could just generate the code and run the code. So there was some nitpicking about, missing the point for, oh, look, if I'm trying to solve this task, this is totally a ridiculous way of doing it. Or, oh, they're penalizing this task and this model because actually it turns out that formulation is impossible to solve. And they're not giving it credit for basically giving up when that's the right answer. And that point, this is a bit of a tangent, but this was some of the work I did in my PhD, which was like, really, how do we get these models to say, I don't know, and believe them, right? Because sometimes that null result, that I can't continue, is more valuable than just charging ahead and blasting through a bunch of tokens and then getting nothing. So I do think that, that question around how do we rate, how do we rank, how do we grade models on these tasks when the I don't know is a valid answer? But that's not codified maybe into the experimental design. So that was interesting. I think, for me, again, I'll repeat it, the big takeaway was that reasoning models can help, and really just making me think about how they work was really the big thing. But that also they're not silver bullets. That, as we know from lots of anecdotal evidence, that people have tried to just take whatever best model is out there to solve their business use case task. And just because it's a reasoning model doesn't mean it's going to work. That your task it's very important what your task is and how you set it up. And I think that's kind of one of the ancillary outcomes of this paper.
Yeah, the discussion and the debate around all this kind of reminds me of the sort of, early 2010s on the web when there were all these like Hacker News debates about programming languages and which ones were best. That you don't see that anymore. But I feel like you have that in the AI space, right? There's a lot of people that want to show that and that think that LLMs are only going to get us so far and they're only capable of this type of reasoning. And we need some other things to happen to move beyond where we are. And then I would say most of the people at the big model labs kind of believe that like scale is going to get us there and we just need more of it. I'm sure there's some naysayers there, but and then there's lots of views that are in between those two in various ways. But it's a pretty heated area of intellectual debate at the moment.
And it's, just to kind of jump on that, there's also the distinction between the, one of the many distinctions between the LLM space and, say, engineering space, right? Like we can argue about programming languages, but it's ultimately a personal preference or a right tool for the right job. But LLMs are still fundamentally actively part of academic research. And those incentives and what people value are different, right? So I'm going to come out here and say, oh, my model did better on this benchmark. My number is higher than your number. That gets me a paper. That gets me to, say a thing. And that's what matters to me is that because that's the currency that I trade in as an academic if I'm doing that. Whereas if I'm like arguing about which database to use, I'm not worried about, mostly it's like, okay, well, what are the features? Does my problem fit that feature? If you're talking about something that's utilitarian and practical or functional, it's a little bit easier to do some of that evaluation and do that feature comparison. But with these models, it's almost impossible because we're using these proxy metrics that are valued by an academic community to just say, well, yeah, you did better, so therefore you get a paper and you can claim state of the art. But what does any of that translate into practical use? And I think that is still a very much open and difficult to answer question right now.
Yeah, so where do we go from here? How do we build more reliable reasoning systems for practical applications?
So, one thing that, again, all this work started for me, and as I've been thinking about not only what, reasoning models, because fundamentally reasoning models, these chain of thought style things, these are a form of test time compute, of inference compute. We are using an existing model to generate more tokens to try to tease out a better answer. And so I think that there's a lot of fertile ground here. But as we were just saying, like, it just seems like there's so many things. It's a lot of like throwing spaghetti at a wall. It's, well, I'm going to try this combination of things and I got this number to go up, and I tried that combination of things and that number went up. But it's hard to know. And so as I've been digging into this work, I've started to think a little bit more about like, is there any kind of theoretical underpinning that we can use to help guide some of these choices? And so how do we think about what these are doing? How do we think about these as decomposable pipelines? How do we think about these from these techniques from a theoretical perspective, which will help us then say things like, well, okay, if this is your task, Maybe we can do a quick benchmark evaluation on a certain kind of model and say, yeah, you know what? There is absolutely no way that this model, through any amount of reasoning or parallel search or anything, is going to be successful. But this model, it looks like through some combination there may be, and we can actually do intelligent search space to figure out where to go. And so I do think that there is real opportunity here around probing what these things are actually doing, trying to think about them more theoretically, and then using that to build more evaluation and sort of foundational frameworks of then how do you deploy these in a practical sense.
Makes sense. So do we want to talk a bit about the product we're working on?
The task that, things we're working on right now is like what I just sort of talked about around some of these ideas, these more fundamental thoughts of how do we incorporate those into sort of a product. And one of the main areas we're starting here is with being able to do experiments. So one of the things that we know is that, again, just like we see with this Apple experiment, in order to know if reasoning models are going to be good for you or any other sort of inference time compute, if any of this stuff is going to be good for you, you need to be able to run evaluations on your task. And this is, I think, by far one of the biggest problems that people are facing is, how do I do this? How do I do this in a way that gets me good results or at least helps me make good choices? So foundational to all of that is being able to run these experiments. And so the first thing that we are building is that experimental platform, both for ourselves to be able to do these analyses, but then also to provide that to potential customers who will be able to then say, all right, I have my data set, I have my sort of qualification for what's good and what's not. How do I then figure out which combination of techniques I should use? And so we are currently building that out so we can then run our own sort of large-scale experiments to then build up that data and that knowledge to then be able to translate that into things that can be used by potential customers.
Yeah, and I think that'll be really helpful for people that want to, that have certain types of data governance issues. And, I have strong belief from talking to lots of enterprises and following the AI space for a decade now that people don't want the big models to own everything and own all their IP, and that's kind of the path that we're going down if we're not careful. There's a lot of companies where their physical process is the differentiator and their secret sauce, and there's a lot of them where their knowledge workflow process is the differentiator and their competitive advantage. And so I think as companies try to move some of that stuff into an agentic format, I think they're going to need tools where they can understand how to take their data, use it with a model, maybe in some kind of inference time compute capacity, maybe in some kind of reinforcement learning pre-training capacity, different formats like that, but where they can own the IP. And I think that's going to be really important.
Absolutely. So that's it for today. The Illusion of Thinking tool is live. Check it out on our GitHub. If you're experimenting with inference time compute or want to contribute, feel free to reach out. Don't forget to subscribe to the podcast and our Substack for additional drops. Thanks for tuning in.
Thank you.